Hello friends, welcome to the last module of power system, starting with today's topic on power equation. So this is coming under the learning level of 1 of Bloom's taxonomy. So here we are going to study the dynamics of the synchronous machine, that is the rotor dynamics of the synchronous machine, and also the power angle equation of a non-salient pole machines. In the last class, we dealt with regards to the unsymmetrical faults. And why does this faults occur? These faults occur because there will be some problem, some disturbance in the system. This disturbance we call it as faults, and they are categorized as the various types of series as well as shunt. So these faults disturb, or before disturbing, when the system assumes the normal position after the clearing of the fault, it is to be uh, it is to be taken into consideration that the system regains its stability. Whatever was the stability or the quality of power before the occurrence of the fault, the same must be resumed after the clearing of the fault. So that is related to the system stability. So the power system consists of some synchronous machines operating in synchronism. For the continuity of the power system, it is necessary that they should maintain perfect synchronism under all the steady state conditions. When the disturbance occurs in the system develops a force due to which it becomes normal or stable. The ability of the power system to return to its normal or stable condition after being disturbed is called stability. Yes, as I told you that after the clearing of the fault, the regaining of the state of the system. Disturbance of the system may be of various types, like sudden changes of load, the sudden short circuit between line and ground, line to line fault, all the three faults, switchings, etc. So let us define some topologies that we are going to use periodically in this particular topic. So steady state stability. It refers to the ability of the system to regain its synchronism, that is, speed and frequency of all the networks should remain same after slow and small disturbance which occurs due to gradual power changes. Steady state stability are further divided into two types, that is, dynamic stability and static stability. Dynamic stability denotes the stability of the system to reach its stable condition after a very small disturbance. It is also known as small signal stability. It occurs mainly due to the fluctuation or load or generation level, in load or generation level. Static stability is referred to that obtains without the benefit of the automatic control devices such as governors or voltage regulators. So the next category of the stability is a transient stability. It is defined as the ability of the power system to return to its normal conditions after a large distribution. When it is a small distribution, it's a steady state stability. When it is a large distribution, it is a transient stability. The large distribution occurs in the system due to the sudden removal of the load, line switching operation, fault occurring in the system, sudden outage of a line. Coming to the power angle curve, let us consider the power equation of a synchronous machine, which is connected to an infinite bus through a transmission line of reactance XL, as shown in this figure. Assuming that the resistance and capacitance are neglected, the equivalent diagram of the synchronous machine connected to the infinite bus through a transmission line of series reactance is shown as this. So E at an angle of del, that is a load angle, connected to an infinite bus with a voltage reference of V at an angle of 0. Xt is the synchronous of the transient reactance of the machine, and XL is the synchronous reactance of the transmission line. So the complex power is given for the generator is given by S is equal to V into I. So S is equal to V into I, and what is I? I is the current that is there. So if we see, the I current flows through XL and XC. So the equation of I in this case will be E at an angle of del divided by x at an angle of 90 degrees plus j v by x. So here we have to split this particular form into the real and imaginary part. So s is equal to ev divided by x at an angle of 90 minus del minus j v square divided by x. There are some changes in the uh, signs, but it will not affect the value of this equation. So that what we get is s is equal to v into ev by x sin del plus j ev x cos del minus j v square by x. So here this P plus JQE, that is the real and imaginary part if we see. So what we are going to have, I think the equation over here is getting a little bit mistaken. So here please do make the corrections. S is equal to, it is EV, the V is not already taken inside, so V is not outside, that is by mistake it has occurred over here. So it is simply EV by x sin del plus J EV by x del minus j v square by x. So only taking the real part, it will become ev by x into sin del. So where the x is equal to xt plus xl. So the active power transferred, let us assume that the active power is transferred to the system, the reactive power is transferred to the system. The maximum steady state power that occurs when del is equal to 0. So when del is equal to 0, the maximum power transfer occurs, and when del is equal to 90 degrees, the power occurs is again ev by x, which is the maximum power. So p is equal to sin, when it is sin 90 it becomes 1, when it is 0 it will become 0. So p is equal to ev by x. So p is equal to pe max sin del. So if we plot the power angle curve over here, we can see over here from 0 to 180 degrees, that is the generator action, and when the del angle becomes negative, the action comes out to be motor action. So the graphical representation of PE and load angle is called as the power angle curve. It is widely used in the power system stability studies. So this power angle is shown as this diagram. So the maximum power is transferred when del is equal to 90 degrees, because sin 90 is 1. As the value of del goes on increasing above 90, the power starts decreasing. We refer to this power as the deaccelerating power and becomes 0 at 180 degrees. Above 180 degrees, again the power becomes negative and starts increasing, which shows that the direction of power is reversed and the power is supplied from the infinite bus through the generator, because now it is the motor action. The value of P is often called as a pull out power. It is also called as the steady state limit, that is SSL. The total reactance between the voltage sources E and X is called as a transfer reactance. The maximum power limit is inversely proportional to the transfer reactance. So to summarize this, we can say that the power angle curve tells us about the electrical power output of the synchronous machine, because now it is moving through the dynamics when the power angle load is varied. Why this angle is varied? Because nowadays when we consider the load is not remaining constant, it is fluctuating. So definitely there will be a change in the value of the angle del. So as the angle del changes, the power equation value also changes. So it can be seen that from this curve that as we increase the del from 0 to 90 degrees, the output increases sinusoidally. This is called as the accelerating power. But a further increase in power angle del beyond 90 degrees, the generator electrical output decreases, causing the deaccelerating power, and beyond which the action no more remains as the generator action, but it turns out to be a motor action. So in the next class we are going to study the power angle equation for a synchronous machine, which is a salient pole synchronous machine. Now the machine which we have considered is a non-salient pole machine where the air gap remains uniform, and therefore the xt is equal to xl over here. But when we consider a salient pole machine, the rotor is not a smooth cylindrical rotor, it is rather a uh, uh, projected. So that we will cover in the next class. Thank you.